Thanks everyone for having me. My name is Tristan from Singapore Nanyang Polytechnic, and the topic I'm going to share about is RFM and classification predictive modeling to improve response prediction rate. So, in consumer electronics, typically the sales cycle is about 2 to 3 years, which is very short, and with increased competition and product differentiation faced by suppliers in online distribution channels, it is therefore very important to pay attention to targeted marketing in online customer electronics sales through the use of predictive analytics. There's a couple of reasons. First, marketing paradigm is not becoming increasingly customer focused. And second, the unsolicited marketing is typically quite costly and ineffective due to low response rate. So in this particular study itself, we look at the online sales channel of a CE company based in Asia Pacific, looking to actually receive higher response rates through targeted marketing for its sales catalog and its upcoming trial marketing campaign. So the data that we have in this trial is 4,000 unique sample customers. We have one target and 15 input variables. The company wants to actually target optimal 450 customers. And the break-even response rate is actually about 6.7%. Okay, so the findings of this study will be useful towards CE online marketers' use of predictive modeling to improve customer development. Now, so we are basically comparing RFM against your classical classification predictive model algorithms, the neural network, logistic regression, decision trees, and your ensemble models. Okay, so RFM is basically a technique which is used that relies on 3 customer behavioral variables. Right, how long since the last purchase of the customer, right, or recency, and how often the customer purchases or frequency, and how much the customer has actually bought or monetary itself. RFM analysis has long been used, and early researchers have shown that RFM can offer a powerful way of predicting future customer purchases. And then we have got your classical data analytical mathematical models, for example, logistics regression, decision tree, and your neural network itself. We find that the logistics regression is actually useful for predictive outcome analysis for dichotomous dependent variables. And the purpose of logistics regression is actually to classify marketing response cases into its most likely category, yes being customer responses to marketing campaigns and no being non-responses, through a logistics function with a set of beta parameters and intercepts. Decision tree is useful for the implementation of rule-based system approach in a tree structure data mining algorithm. The ease of model explanation and reusable set of rules actually gives it a relative advantage in its use in understanding and predicting customer behavior. And then we have neural networks, which is useful for prediction problems where no mathematical formula is known that relates inputs to outputs. And prediction is actually more important than explanation. It is known for its ability to train quickly on sparse data sets. And in this study, we actually utilize a universal approximator, which is a feed-forward artificial neural network known as multi-layer perceptron. For more robust prediction and classification, ensemble models are basically used, and they are a product of basically combining 2 or more models that are adequate and discordant to achieve high accuracy, reduce biasness, and reduce variance. So in this case of dichotomous class variables, we use averaging ensemble method, where the input model's posterior probabilities are averaged. In this study, we investigate 4 ensemble permutations of the 3 former classification methods, namely the logistics regression decision tree ensemble, the logistics regression neural network ensemble, the decision tree neural network ensemble, and the logistics regression decision tree neural network ensemble. So some pre-analysis of the key variables. So we look at the first chart on the top left-hand corner. We can see that total purchases, T spent, and also monthly LP, which represents your your frequency, monetary, and also recency. They occupy the first, second, and fourth position in terms of the total worth. And as well, at the bottom left-hand corner, we can see that the Pearson correlation coefficient between the total purchase, which is your frequency, and your monetary or T spent, is basically very strongly correlated and with highly statistical significant p-value. In this particular data set as well, we also see T total purchase and T spent exhibiting highly positive skew, and this is quite prevalent across your RFM studies. And in order to actually rectify it, we need to normalize the data. Now, RFM, decision tree, and logistic regression actually are unaffected by non-normality of data sets. But in this particular case, because we are using neural network, and it's very affected by non-normality and also outliers, so therefore corrections will need to be done to ensure that the data set is correctly normalized. So RFM modeling is actually being done here. In this particular case itself, of the 125 bins, because each variable actually have 5 bins from 1 to 5. So 5 to the power of 3 with 125 bins. The output shows that there are 88 filled bins with only 43 indicating mean response rates that's greater than about 6.7% break-even response. To remain profitable, so therefore they need to target these bins. We sort them in accordance to descending order. And we find that the bins itself, basically, we can see from the left-hand side, the stack input, one being labeled orange, which is yes response labeled orange, and the blue response, then no response, which is labeled blue. We can see that 050505 has the higher frequency, and its mean response rate is actually about 47% from this table to the right. And then 050504, it actually is not very high in terms of frequency, but its mean response rate is actually quite positive, and we can see from right it's about 37.7%. So from this table at the right, what's being done is that we actually sorted the RFM bin in terms of mean response rate from highest to lowest, and we computed the cumulative frequency, where the first top 450 customers are actually being computed. And from here we see that the total customers that responded yes are actually 193. So 193 out of 450 is actually 42.9% of response rate, which is about 6.4 times improvement from the break-even response rate itself. And then in terms of classification predictive modeling, now a couple of things needs to be done. First of all, the response target variable, where your class member yes represents 1 represents yes and no represents 0. Of these, 84.7% is actually of class member yes, and 15.3% is of class member no. So as you can see, this is a classic imbalance data set, which can lead to biased prediction and misleading accuracy. And as well, this is a multi-dimensional data set because it has 15 independent variables and 1 target variable. So therefore, in order to correct for this highly imbalanced data set, there's a few ways that we can go about doing this. First, we can apply random oversampling of classes with lower frequency. Second, we can apply random undersampling of classes with higher frequency. And third, we can actually undergo synthetic minority oversampling technique, or SMOT, which is a modified oversampling method that creates new synthetic observations based on minority class observations and its nearest neighbors. So in this particular case, we actually exclude the use of SMOT because of the high dimensionality, and we apply a blend of the methodology used in a couple of papers in your Wang, Li, and Wei, and also Fu, Zhang, Bai, and Sun, which uses a combination of principal components analysis, PCA, for dimensionality reduction and undersampling the majority class observation to attain 50-50 majority-minority balance. So in this particular case, PC actually generated a selection of 13 variables without significantly reducing the explanatory power of the model. The total variations explained by these 13 variables are 96.7%. Okay, now the classification prediction modeling results are now, we can see from the right-hand table. From there we can see that neural network actually performed the best, about 86.8%, followed by ensemble models, and then followed by decision tree at 84.7%, and followed by logistics regression. This is summarized actually at this table to the top. And in order to improve the prediction results, we undertake appropriate probability cutoff point at 0.53 or 0.57, as can be seen from this table at the bottom. And this yielded enhanced overall correction classification rate of 87.2%. So we adjust the cutoff probability to 0.53. So in terms of the actionable insights, we can see that from this results itself that the neural network model actually showed improved accuracy over RFM from 42.9% to 87.2%. So this validates results of earlier studies and showed that the proposed predictive model can be used to improve performance of response prediction rate targeting. And interestingly, while the ensemble models are expected to perform well, they did not appear to have significant improvement of results, with accuracy rates ranging from 85.5% to 86.6%. And in addition, applying the neural network model also sacrifices explainability power. So in this particular case, we might want to use the decision tree model for marketeers because it provides clearer descriptive reasoning with associated rules, although it loses about 2.5% in terms of predictive accuracy. The logistics regression actually fared the worst amongst the classical prediction models at 83.2%. In any case, its explainability power is actually lower than decision trees, although it does have some interpretability for practitioners with statistical backgrounds. So for the RFM model, aside from this poor response prediction rate, it also suffers from other disadvantages as well, which makes it less desirable for use. For instance, the data manipulation actually required is quite significant. And then also as well, the RFM variables are not, they exhibit high interdependency, especially so with the correlation of monetary and frequency variables. So in this particular case, there were some papers that actually proposed the use of collapsing monetary and recency into one variable, which has led to improvements. However, its performance is actually significantly lower than logistics regression and decision tree models. Now, in terms of implementation, it is imperative, it's important that the company actually understands that this classification power of the models and the marketing campaign targeting is actually a continuous improvement process. And this process improves with every iteration from the baseline towards its objective threshold level that's set by the company's management. And as well, false positive transactions should be investigated with the effect of incorporating the findings to improve the model going forward. Also, to improve model accuracy, the marketer or data scientist can actually look at a combination of different methods. For example, classification approach as showed in this paper, rule-based approach, such as encoding knowledge of well-defined patterns into model application codes. The clustering or density-based approach, such as identifying response rate conversion that belongs to the furthest distance kth neighbor. While taking into account that positive response rate detection typically entails modeling imbalanced data set which can affect model accuracy. It is also useful not to consider input variables in isolated manner, but consider them in a domain contextual manner. So you might want to look at, for example, the happening of a certain retail event versus sudden change of online consumer electronics retail behavior associated with high rate of change of these transactions. Incorporating a deep retail domain expertise to the model construction can help significantly improve the accuracy of the targeted model customers with high response rate. So that's the end of the presentation. I've got a couple of questions actually from the TPC community that I'd like to look at. So one is actually commenting on the cold start problem in the response prediction. So cold start problem is basically the problem where there's insufficient data with regards to users and items in recommender systems. For predictive modeling, unfortunately, you would have to look at competitor data or even purchasing data from, nowadays there's lots of data companies that provide so. And then subsequently, as you build sufficient data, customer traction, you would then be able to use these customer database to do your predictive modeling. Unfortunately, the data is idiosyncratic. Whichever analytical analysis that you actually do is specific to your company itself. So therefore, you would still need to build your own database in order to have analytical prediction that is contextual to yourself. In addition, you can also use data augmentation as well. For example, using alternative data like social media data and so on to improve your data analytical data analysis. Now, the second question that I've gotten from TPC is that if a user just bought a dishwasher, does it mean it likes dishwashers, and is it likely to soon buy a new one? How do we combat these kinds of prediction problems? Now, so for this particular case, this question is more related to association analysis and recommendations. So for example, in the context of, for example, buying of consumer electronics, if you know that this particular customer just bought this dishwasher, and in a context where the customer actually has moved home, it might be possible that this customer actually would like to buy other kitchen white goods, like for example, your fridges, your dryers, washing machines, even your grills, rice cookers, your blenders, and so on. And so therefore, if you have already known that this customer has purchased this particular product, you might want to do association analysis, your market basket analysis, and then from your recommender system actually provide a suitable recommendation to this particular customer itself. Now, if the customer has not bought it, you might still want to extract this information through, for example, cookies or the data that you can crawl from your app or other online sources. Where if you find that this customer actually has done a search for this particular product, you can then do targeted marketing to this particular customer so as to be able to then do the right recommendation to this customer, for example, to buy a dishwasher or other kitchen white goods, for instance. So that's all I have in terms of questions for this presentation itself. Thank you very much, and I hope to see you in the next ZINC presentation. Thank you.